Ready? Okay, so we are almost at the point of making nice movies, which is always a good thing. So what we're now going to do is we're going to use our representation. We're going to say that it's valid all the way through the mantle, and we're going to perform this procedure that's called downward continuation. So let's go back to our equation 10. That might be a long way in the past. Equation 10 is oh gosh, there. So equation 10 is our internal representation of the field, and if we now, so we're claiming that this is valid everywhere, both outside the Earth and also throughout the mantle. So if we now put the radius r to be something less than the radius of the Earth's surface, then this number here obviously becomes larger than 1, and it is raised to a power of L plus 1. So that then becomes a factor which multiplies these Gauss coefficients and the spherical harmonics. The higher L is then higher L terms are then disproportionately amplified with respect to the low L terms. But that's actually exactly what we need to be able to represent the field at the core surface, because we are then going closer and closer to the source. So actually what we see are smaller and smaller scale structures, and in fact if you put so I haven't written this down, have I? No. The radius of the core for all intents and purposes is so C is 3485 kilometers, and remember we had A is 6371.2 kilometers. So that the ratio of those two numbers is about 1.8. So the higher degree terms are amplified with respect to the lower degree terms. So when we do that, let's go. Let me just do this for one particular time. So if we actually perform this and look at what the magnetic field looks like at the core surface, it looks something like this. This is now for the year 1980. So this was performed using MagSat data. And it's images like this which has really conditioned our thinking, I suppose, for the last 20 or 30 years, because of the features that we see. So this is now the radial field intensity at the surface of the core. So it's what we're seeing is the number of field lines per square meter which are emanating out of the core. So the red stuff is coming out of the core, and the blue stuff is field lines going into the core. And you can see that there are these concentrations of field, very intense. There are certainly 4 clear ones which live at high latitudes, and then there are these other concentrations which live here near the equator. And you'll also see that in the southern hemisphere is this blue patch, which is a patch of reversed magnetic field, reversed with respect to what you might expect. So if you had the so-called dipolar model in your head of what the field would look like, the dipolar model would have an entirely blue northern hemisphere and an entirely red southern hemisphere. Indeed, it would have contours which gradually become more and more intense as you go to the poles. So it would be a nice, simple, increasing pattern. And you can see that that is not what we see. And in fact, this is much more interesting. And well, we'll talk in a moment about what we think this tells us. Okay, but anyway, that's our first look at the magnetic field at the core surface. Now I'm going to give you some details of how we analyze data, what data are available, and how we analyze data for the last 400 years, because my colleagues and I created a model which is called GUFM1, and oh gosh, it's freely available. It's freely available to the community. GUFM1, okay, and it represents the field from the year 1590 to 1990, so it doesn't quite go to the present day, and it's based on lots of different types of data, and maybe I'll leave this slide for you to read at your leisure, because it's not so interesting. So this is the kind of data distribution that goes into this model GUFM1 starting in 1590. I mean, of course, it goes without saying that you go back in time and there are fewer and fewer data available, gradually increasing out to the present day. And the kinds of data that it relies on from the very earliest times it's mostly ship data. So the ships were, of course, measuring declination for their own purposes, and they dutifully wrote it all down in the logs. And the declinations are very useful for recreating what the field looks like. We've seen that the declination is quite heterogeneous on the Earth's surface. And you can see, so this is where India comes in, because a lot of the data come from the trading routes which were going between Europe and India, starting in the 17th century and going all the way on till, well, typically the middle of the 19th century. So there is there's a big data set that's published by in Art Jonkers's paper, and all the data are freely available to anyone who wants to use them. So that's the kind of distribution. I mean, I've plotted them all there for 100 years. You can see that if you take 100 years, you get quite a good distribution. Of course, when you start looking at each decade, of course, it becomes much more heterogeneous. But that's the kind of data distribution that you can rely on. So let us now just have a quick look at this model. Is it this one? Yeah. So this is the model GUFM1, and I'm going to play you this a few times. So it's the same kind of model that I've already shown you, and the first thing to recognize is that very, very far back in time, of course, the data distribution is much poorer than at the present day. The accuracy of observations is not so high, and so you have a much smoother a representation of the field. You have less resolution in the field than the present day, but you will nevertheless, you'll see features back in time that look kind of familiar. We're already back in 1595 here, and you'll see that here in the southern Atlantic there is this feature which I've already pointed out, this reverse flux feature. So there are a lot of features that you'll see that are in common. I'll play this movie a few times. For example, take a look at this spot here which starts out life just beneath India. Of course, this is at the core surface. The continents are just for reference. There's no continents at the boundary of the core. But so take a look at this spot and see how it evolves. Also, you'll see that although they're not terribly well resolved, you see these 4 spots at high latitudes. So let's play the movie, and then we need to look at it a few times to... what happened there? I didn't do the right thing. So here's this spot which starts out beneath India and gradually drifts all the way over Africa. As soon as you get towards the mid-19th century, you'll see that the resolution really looks improved. So here we are, 25 years ago. Here are these 4 big spots living at high latitudes. Here's the intense features living at the equator. Here's the big reversed flux patch, which is living in the South Atlantic. I'll play this again, but you'll see that nevertheless there's a lot of coherency in what's happening. For example, follow this spot, which starts out life here and gradually, well, it sort of wobbles around, but it gradually drifts westward. So this is sort of the, if I dare say it, the sort of definitive representation of the field for the last 400 years, and it kind of gives us some insight as to what's been happening. There are some funny features. For example, here at the North Pole, you'll see there is this orange spot. So that's either a reversed flux, or if you want, it's just a low in the field. So the field is very intense here and here, and very weak down here. And in a similar vein, it's kind of weak here at the South Pole.
This is just to remind also some
normal components. So this is the radial field. So this is the number of flux lines per square meter coming out of the core. So it's coming out here, and it's going back into the core at the top. Yeah. So we use, I mean, I'm going to, very rapidly, I'm going to start to allude to things that Alex talked about this morning. But if you remember in the zero diffusivity limit, the eta is 0 limit, Alex showed you this morning that the field lines get frozen into the fluid and will tend to move along with the fluid. So what we're going to do is we're going to use a lot of these features along with that high magnetic Reynolds number idea. We're going to use those features to try to see what the fluid flow is like. But at the moment, we just have these things sticking out of the core like a hedgehog and being advected along by the flow, we think, at least to first order.
Do we know whether these reversed regions are coming out all the way out of the surface, or are they just local loops?
Well, some of the field lines won't make that. Well, no. Let me think about this. Just give me a moment. I mean, they are local loops. For example, these kind of close on themselves, but it's in a way it's sort of a bit matterless, really, whether or not they.
Yeah, I just reconstructed from the surface to the core. So you'll have all the information in between.
Yeah. All we know is that the field lines make it out of the core. I mean, you can certainly trace a field line, and you will find that, in fact, they will close on themselves typically. Yeah.
Just curious.
Right. Let's just go back to this and. So one of the things that was said in the early 1990s probably is when these first sort of images were made, this is from work of Bloxham and Gubbins, the kind of interpretation of this structure is probably the following, that these patches are how can I put this? They seem to be sitting just outside the tangent cylinder. Now, the tangent cylinder is a cylinder which just fits over the inner core. So the inner core is a small ball of solid iron in the center of the core, about the size of the moon, and it's about 1/3 of the entire size of the fluid of the total core. And if you just set a cylinder which just inscribes the inner core, then at the surface of the core it would look like that. It has a certain angular displacement. And it was noticed that it's intriguing that these flux distributions sit just outside the tangent cylinder. Now, I wasn't here first of all, but I think did you talk about the Proudman-Taylor theorem, Alex, or no? It's coming up. It's coming up. Okay. You will find Chris will tell you really what the kind of dynamical interpretation is of this of these things, but they look like they're concentrations of flux which are sitting just outside the tangent cylinder here, and they're part of the dynamo process. That's what we believe. And what's more, the fact that the field is weak inside the tangent cylinder maybe says something about the dynamo action that is taking place just above the inner core. But I think you'll agree that it's intriguing that you have that low field there. Okay, so now let's just finish off by talking about what we can derive sort of as secondary products from this kind of field model, such as GUFM1. So if we, yeah.
There are two Taylor columns sitting there.
Yeah.
From the observation.
Yes. I don't know if I want to say more about this, but I think Chris is going to talk to you about the Proudman-Taylor theorem, and so just bear in mind the observations for tomorrow. I think I might say a little bit myself, but yeah. So we're going to see how we can make use of this. We've now got a very convenient representation of the field and its evolution. We'll see how we can make use of this. So here's a little summary of what I've just told you. We've got these strong flux spots over Canada and Siberia with their counterparts in the southern hemisphere. So we have this strong symmetry across the equatorial plane, which is seen throughout the historical record. We've got the high latitude flux spots sitting just outside the tangent cylinder, and we have this low flux at the North Pole, which seems to be consistent with the projection of the inner core. Now, let's see what we can do with this. It was very much an activity that began in the 1960s, the question of whether you could find the flow at least at the top of the core. So the question was, could you find the flow V that is in the magnetic induction equation here that is responsible for the secular variation? So we've now got observations of dB by dt, the rate of change of the magnetic field with time, and can we find the flow that is responsible for that? Okay, and I've said the immediate problem is we don't know all the terms that contribute to this term here. But there's a way around it. So the way around it is this idea of the frozen flux theory of secular variation. So it's using what Alex said was Lundquist's theorem, really, I suppose. So the idea is that you drop the diffusivity, or the diffusive term here, and that's done on very justifiable grounds, which we'll try to justify now. So let's just look at the time scale.